are now entering the advanced material zone. Your mission, should you choose to accept it, is to discover how to make the windscreen for a supersonic jet, to understand why the material in a heat shield protects a spacecraft re-entering the atmosphere, to design a bulletproof vest, and to understand these properties. Unlike these advanced materials, this tape will now self-destruct. There doesn't seem to be that much choice when it comes to choosing the material for a windscreen. It's got to be transparent. But we don't often think of transparent materials as strong. The biggest danger to pilots are bird strikes. Being hit by a bird at hundreds of miles an hour is no joke. Normal glass shatters easily, but some glasses are much stronger. This is how an aircraft windscreen is tested. The red package has the same mass, density, and composition as a bird. But how can we make glass that strong? First question, what is glass? Here's the raw material, sand. A mixture of compounds, but mainly silicon oxide. It's mixed with sodium carbonate and recycled glass, then heated to 1,300 degrees Celsius. Glass is a mixture of salts called silicates. But why add the sodium carbonate and old glass? Because it lowers the melting point of the mixture, saving fuel and money. But how is this molten glass turned into flat sheets? Strangely enough, by cooling it on a bath of liquid tin. Liquid tin and glass don't mix, so the glass floats. But it solidifies at a temperature when tin is still a liquid. Most glass is now made in this float process, but you recall the problem with ordinary glass. It shatters easily. Every knock puts it under tension and it cracks. But what can you do about a material that's weak under tension? Another window, this time from a car, but watch. You have to hit it harder. But that's not the only difference. The fragments are smaller, not as sharp, safer. So what's happened to this glass? Is it even the same material? Better take a look inside the factory. Highly automated, but it arrives at the production line as ordinary sheet glass. It's cut into the basic shape, but there's nothing that could make it tougher here. But then it's heated. Glass won't melt at this temperature, but it will soften. So what's going on? As it emerges from the furnace, jets of cold air are directed onto the glass, cooling it very rapidly. But heating, cooling rapidly, why should that change a material's properties? Well, what happens to something when it is cooled down? It contracts. But what happens when you cool something quickly? Look at it in cross-section. Now let's go through the process. The glass is heated, then cold air is blown onto the surface. So what happens to the particles within the glass? In the hot glass, they're evenly distributed. The glass is uniform. But the cold air causes the particles at the surface to move closer together. They concentrate. This puts both surfaces of the glass in a state of compression. Normal glass, weak under tension, but toughened glass, surfaces under compression. So it's stronger. It is the same material, but it's up to 4 times as strong. But it still shatters. This glass doesn't. So how's that been treated? Not at all by the look of it. 2 sheets of raw glass. Funny, everything seems to happen in pairs. But why should two pieces of glass be any advantage? Why not use one piece twice as thick? The two plates of glass are heated to shape the windscreen, but cooled slowly, so they're not toughened. But here's something different. It's not only that there aren't any robots in this dust-free environment. A plastic sheet is sandwiched between the two pieces of glass. The windscreen is laminated, made up of more than one layer. But plastic sheet doesn't look very strong, isn't very strong. So how can it make the windscreen stronger? And why take so much trouble to make the room free of dust? Well, here's the answer to that. The air is squeezed out of the sandwich. Wouldn't want any dust particles in your windscreen, would you? Then the whole assembly is put into a pressurized oven, an autoclave. This melts the plastic, bonding it to the glass. Coming out of the oven, at least the windscreen's clear. You can't see the plastic layer at all, but still no clue as to why it might be stronger. Hit it, and the cracks don't propagate far. It certainly doesn't shatter. But the glass has only been shaped. Otherwise, it's untreated. It must be the plastic. Cracks form because of concentrations of pressure. The outer layer of glass does crack, but the crack stops when it reaches the plastic layer. Glass is rigid, but plastic can be compressed, spreading out the force of the impact. No concentrated force, no chance of the crack spreading. Toughening and lamination, two different ways of making glass stronger. So how about stopping bird strikes? Obvious. Combine them. Aircraft windscreens are air toughened and they are laminated. This time with several layers of glass and plastic. But that's not all. The glass is also toughened chemically. It's dipped in a concentrated potassium solution. Glass contains sodium ions as well as silicates. The sodium ions near the surface exchange places with the potassium ions from the solution. But the potassium ions are larger. They pack the surface particles closer together. We've seen that closer packed particles means compression, and compression means toughened glass. But this is toughening at the molecular scale. Now it will stand up to a 500-mile-per-hour bird. Just in case you ever find yourself in the appropriate situation, there are two really dangerous moments in a spaceflight. At the launch, you might get blown up by your own engines. But just as dangerous, and a bit more difficult to see, is re-entry. The friction between the spacecraft and the atmosphere produces heat, hull temperatures of thousands of degrees. But what sort of material can stand up to that? Certainly not a metal. Over 1,000 degrees and many metals melt, like this iron. And if they don't melt, they become much weaker, as this graph shows. Certainly don't want the spacecraft falling apart. So we can't trust a metal. But hang on, what's that crucible made of? The one holding the molten iron. Might not look like it, but it's a kind of pottery. Look at this. A tunnel kiln in a large China factory. It's 1,300 degrees Celsius in there, and an ordinary dinner service can take it. Both the dinner plate and the heat-shielding tiles on the space shuttle are ceramics. So what's a ceramic? They wouldn't let us into the space shuttle factory, so how about the dinner plate? It starts off as china clay, mined as a mineral. Different clays are mixed together for their different properties by suspending them in water. Then the particles are filtered out. Now the clay can be worked. But at this stage, it's still fundamentally the raw material. Doesn't look like it can stand up to anything. So where does the transformation to a ceramic take place? First, the clay is pressed into the desired shape. This brings the particles closer together. Then it's heated to a very high temperature. What happens to materials at high temperatures? The particles vibrate more. Where they touch, they rub against each other. It's similar to friction welding. But at even higher temperatures, the particles fuse together. When the ceramic cools, it has become a solid mass. Once that's happened, patterns and glazes can be applied to the finished pot. That's fine, but why is the finished ceramic able to withstand such high temperatures? The key is in the kiln. Like all minerals, clay has a very complex chemical structure. It contains aluminium, silicon, oxygen, and water. But we can simplify that structure. If we take a single particle, on the surface are silicon and oxygen atoms. But silicon and oxygen can form a very stable structure, a pyramid with one silicon atom at the center bonded to 4 oxygen atoms. But these pyramids can link together to form a huge lattice structure, and every bond is strong. The silicon and oxygen form a giant molecule. The mineral quartz is a pure form of this structure. Dinner plates aren't made of quartz, but at the very high temperatures in the kiln, a giant lattice is formed by the silicon and oxygen on the surface of the clay particles. Ceramics are resistant to heat because of the strong bonds within these giant structures. So where else could we take advantage of this property? Jet engines run at high temperatures, but the higher the temperature, the more efficient the engine. Most jet engines run at about 900 degrees Celsius. If only we could increase the temperature to 1100 degrees, fuel consumption would be decreased by 15%. Good for the environment, good for ticket prices. But what are the engines made out of? Metal. And we know what happens to metals at high temperatures. They become weaker. Looks like we can't save that fuel. But could we make parts of the engine from ceramic? It's a nice idea. These metal turbine blades would be the obvious candidates for replacement. Right in the hottest part of the engine, made from ceramic, and they'd save weight too. There's only one problem. Just like cups and saucers, experimental ceramic turbine blades are brittle. But if ceramics have a structure that makes them so resistant to heat, why are they brittle? You might have spotted the answer already. Even after firing, there are tiny holes or pores in the structure. Hit a ceramic and forces become concentrated at these pores. Cracks spread. But brittleness isn't always a problem. Watch this. Yes, that is a bullet. And that's a ceramic tile. It shattered, but the bullet didn't penetrate the backing plate. Why not? What happens when something shatters? Energy is transferred from the bullet to its target. A bullet has a lot of kinetic energy. You can see how much by firing a bullet at a very heavy pendulum and observing the movement. A bullet has a mass of 30 grams, but this pendulum weighs 30 kilograms. To stop a bullet, all this kinetic energy has to be transferred. Some of it is transferred as heat, but the remainder is transferred to the surface of the ceramic, shattering it. Breaking the ceramic takes a lot of energy. Compare ceramic plates with metal ones, and you can see the advantage. The bullets pass straight through metals, such as aluminium or steel, And in case you don't believe it is ceramic, it even sounds like it. And think of an old suit of armor. Ceramic has other advantages too. All right, so stopping a bullet with an advanced dinner plate is quite unusual. But at least a ceramic is rigid. How about stopping a fast-moving projectile with a fabric? Sounds unlikely? Well, watch this. Goes through the top layer, but doesn't come out the other side. Okay, so it's not a bullet. But this kind of small fragment has the same velocity and mass as those produced in an explosion. 10 layers of what looks like ordinary fabric can stop a fragment, but even twice as much wouldn't catch a speeding bullet. Would it? Of course not. But unwrap the fabric, and there it is. Flattened, but definitely the same bullet. So this ordinary artificial fabric can't be so ordinary after all. It looks like nylon, and it's woven like nylon. So what's the difference? Artificial fibers like nylon are polymers, long chain molecules. But even though the chains are long, each one is only a fraction of the length of a fiber. The bonds within each chain are strong, but the fiber can be broken by pulling the individual chains apart. But this fiber, Kevlar, is different. It's called a monofilament. Each fiber is made up of continuous chain molecules. Each chain is as long as the fiber itself. All the bonds are strong. But how does it stop the bullet? The fibers may be strong, but they aren't rigid. They catch the projectile like a net. The kinetic energy of the fragment is transferred to the fibers, stretching them. So the network of fibers absorbs the energy like the strings of a tennis racket, literally catching the speeding bullet. But monofilaments are useful in making the frame of a racket too. Play tennis a lot and you stand a good chance of suffering from tennis elbow. Every time you hit the ball, the racket vibrates, and that's a lot of energy. Where does it go? It's transferred from the racket up the player's arm to the elbow. Where it causes the bones to vibrate against each other, the joint becomes inflamed. Tennis elbow. But does it make a difference which racket you use? Let's test it. First, a wooden racket. A force transducer is strapped to the handle of the racket. Vibration from there would be transmitted to the player's arm. If we suspend the racket and hit it with a ball, we can measure the vibrations as the racket falls. So what do we find? The ball hits the strings, and vibrations are produced. With a wooden racket, the vibrations decrease, rapidly at first, but then more slowly. Now try a metal frame. Very popular, until recently. See if you can work out why. There's the pattern of vibrations. Think of the amount of energy transferred to those elbow bones. Now a frame made from a monofilament, this time carbon fiber, set in a polymer matrix. The vibration decreases to almost nothing very quickly, and that's good news for anybody suffering from tennis elbow. Like many advanced materials, carbon fiber may have been developed for other, less peaceful uses. But over half of worldwide production now makes nothing more dangerous than tennis rackets and golf clubs. Mission accomplished.